Hello, my name is Kumar Perumal from the University of Bristol, and my topic is clearing and unveiling the impact of indoor air quality in human health. Okay, in this presentation, I'm going to explain why indoor air quality and what is PM 2.5 and my experiment design, and some of the experiments I have done in the chamber, and some of the experiments in building and the results, and e-cigarette experiments which I've done the past week for the UKHSA, and my next step in my project. So why indoor air quality? As we know, like we spend 90% of our life spent indoors, and during COVID-19, this percentage should have increased. And we also know like more pollutants are there indoors than outdoors because of the ventilation. And some of the common indoor air pollutants from airborne particles, indoor formaldehyde, household odor, ozone, and carbon dioxide affects us greatly, like such as confusion, headache, anxiety, and more commonly like COPD, asthma, heart ailment, lung infection, and so on. So this is a literature review I've done as part of my thematic project Vatican. So this literature review was found like 39% studies emphasize PM 2.5 as the primary indoor pollutant, supported by strong evidence demonstrating its adverse effects on respiratory and cardiovascular health. And also when we in figure 4 illustrates that respiratory disease was a focal point in 68% of the publication, and doubly respiratory disease stand out as the most extensively researched topic in this field. So next slide is my experiment. So I'm going to explain the setup and aerosol generation using sodium chloride and some of the chamber experiments, building experiments, and understanding indoor ventilation through carbon dioxide decay experiments and e-cigarette experiments which I've done at UKHSA. So this is aerosol generation and measurement setup, which I'm going to use for my PhD. So I'm using TSI 6H atomizer to generate aerosol from sodium chloride solution, which also the diffusion dryer. And these aerosols are measured with these different instruments. So most of them will know all these instruments such as Decate LP, CPC, the Strack TRX, Alpha Sense, OPCs, and Prem SMPs, SMPS, and C. So these are got like different size ranges, as you can see from this table, and the principle is a bit different, and also the measurement is a bit different. For example, Decate is particle size distribution, and CPC can do particle concentration for things. So this is chamber experiment setup. So I got a chamber made of glass fiber, and this is the volume like 0.36 meter cube. And the 16 atomizer generates the aerosol that goes to the diffusion dryer and then get pumped into this chamber. And then the aerosol here is will go through this will go to CPC and LP, and the data is generated. And this is data generated using Decate LP, which shows 2 different salt solution and sucrose. And from this, I've chosen sodium chloride, which I can aerosolize in an indoor environment. And this is one of building experiment setup which I've done 2 weeks before. So what I've done is I've placed different instruments, such as we got 5 OPCs and 2 CPCs and LP, OPS, SMPS1, 2, and the Strack, everything around the room. So I generated aerosol using 5% and sodium chloride, and was generated for 15 minutes. And after that, these instruments started recording for the data and for the size distribution and the concentration. So I'm going to just show the data which is processed, and this is work in progress. I get to analyze the data and compare the data. So you can see like these OPCs are in different sections of the room, and you can see like which is a bit far away. You can see the concentration is a bit lower and the concentration higher on the other side. This is data generated using the Strack TRX, and the pattern is similar, but and also the CPC here, like it started a bit late. That's the reason it is called this kind of, yeah. And this data generally using LP size distribution. Most of the size distribution is within like less than 2.5. So on this carbon dioxide experiment, which I've done in collaboration with Trina. So in the recent literature, came to know that atmospheric carbon dioxide increases aerostability of SARS-CoV-2. These experiments are really good. Like it shows the ventilation rates of a room. For example, in a room, you measure a certain amount of carbon dry ice. Depending on the size of the room, then spread across the room. Using carbon dioxide sensors, you can see the decay rate, and from there you can understand like if the decay rate is higher, it indicates more effective ventilation of the room. If there is poor decay rate, such as inadequate ventilation and the poor air quality of the room. And once you get the decay from there, you can fit the curve, and that gives you a time constant value, and from that you can define the air change rate of the room. And this is the last experiment which I've done a couple of weeks before at UKHSA using conversion Venus 500. So this is size distribution of two power settings used in weight with 3 different flavors, and which each different flavor has got same components, but only difference between the concentration of the nicotine source. Nicotine source will be different, and also the flavoring agents are different. But that's gives you a difference in the concentration and bit of size distribution as well. So this is this was released during as part of the World Health Day, and I also involved with this project. There's a building called Bristol Digital Future Institute in Bristol, and we have installed like nearly 8 sensors, 6 outside the building and 2 inside the building. And these sensors record temperature, sound levels, CO2 levels, carbon dioxide, and small particles in the air, such as PM1, 2.5, and so on, PM10. And we have been monitoring this since June 2023. And one of the interesting data which I've received last year was during fireworks fiesta in Bristol. So this fireworks happened like nearly 5 miles away from this building. But that day you can see there's a increase in particle level, PM2.5, and this is from the outside sensors, and this is ground floor sensor. And during that time the building was closed and no one was there. But you can see like it takes 6 hours for it to clear. For particles inside the building, it took nearly 8 hours. So it shows like the ventilation in the inside the building this affects the clearing rate as well. So my next steps will be trying to compare tracer gases with aerosols. So tracer gases will be released and captured at different locations at various time series, and comparing them with aerosol dispersion. So we plan to do this experiment this summer in different settings such as house, lecture theaters, and office, etc. And I know like we have a leading instrument companies present here, so it would be great if you have got any latest like instrument to measure PM 2.5 or less, then I'll be happy to collaborate with you. Nice. The next step will be generating aerosols with various size distribution by reporting the airflow and experiments with charged and uncharged aerosols, and also completing my HSF placement on e-cigarettes and exposing them to cells. So that's everything for me. Thank you. I want to thank everyone here and the aerosol team for continuous support, and my supervisor James Matthews for support and help.
Thank you, Prem. Any questions? First one, this is awesome.
was great. You did the PhD. I wish I did. The chart on indoor aerosol is an interesting thing. Why is it you're looking at electrical charge in the indoor aerosol environment? Where do you suppose that charge might be coming from, and why do you think it's significant?
At the moment, what I plan is I'm planning to charge the aerosol and then see the difference. So from there, we can like analyze the data. So at the moment, it's just we are planning. So once I have done the experiment, then I can understand it better.
Okay, another question?
Just quick clarification. Thank you for the interesting presentation. I was wondering, the two experiments you showed in the chamber, were they ventilated? In other words, were there any flow of air?
The flow of air is from the LP, like getting out from the air, but there's no like any kind of external ventilation or anything from tube connected to the LP.
And my second point is, the sampling was done from a single location or multiple location?
For the room is from multiple locations. So
I'm talking about those two chambers experiments you showed.
okay, two chamber experiment is from a single location. It's not one.
Okay, beside, but
So it's like a small box. So I just the sample is taken from the box through the tube to the tubing into the LP. So this the single location. So
thank you.
Great. Well, thanks again.